Hi, today we're going to talk about how to find concavity intervals and points of inflection by using a second derivative number line. In the previous video, we discussed what concavity and points of inflection were. Now we're going to talk about how to do this just using the equation of a graph. We will not need the graph itself. The procedure is parallel to the procedure in the last lesson. That refers to 4-2, where we found intervals of increasing and decreasing behavior and points of relative max and min. Right, it says right here. Using a first derivative number line, which is also known as the first derivative test. Without further ado, determine the points of inflection and discuss concavity for this graph. First things first, we're going to talk about the domain of f. The domain here, I don't want to use that color. The domain here would be all reals. Check. And now we're going to need the second derivative. The second derivative is a very easy process. We find the first derivative, 4x cubed plus 3x squared minus 6x plus 0. The derivative of 1 is 0. And now we look for the second derivative, which means we just do it again. 12x squared plus 6x minus 6. So now we're going to do everything we did in lesson 4-2 except to f double prime. Meaning we're going to set f double prime equal to 0. So that's 12x squared plus 6x minus 6 equals 0. Factor out a 6. It will help you. To x minus 1, x plus 1. Careful when you're solving. X equals 1/2. And -1 are our two solutions. F, I don't know why I did that. F double prime of x will never be undefined. Why? Because it's a polynomial. That leaves us with the possible points of inflection at x equals 1/2 and -1. So that's the possible points of inflection. Okay, that's that. So now, these are really the critical numbers of f prime. But that's really confusing because we use f prime to find the critical numbers of f. So we're going to stick to the terminology possible points of inflection. So just like before, we make a number line. We label it f double prime. We write our possible points of inflection on this number line. And we test the sign, this time of f double prime. So, over here, -2 into the factored form, usually easiest, positive, negative, negative, means we have a positive f double prime. 0, positive, negative, positive, multiplies together, they make a negative number. 1, positive, positive, positive. You should be able to do it that quickly. Careful. Careful. Because we're talking about f double prime, and we have f double prime being positive, we will have what's called concave upward behavior here. So sometimes we draw a positive concave upward shape to make us remember, to help us remember. Honestly, if you can draw these shapes, you probably already know what you're talking about. This is less of a memory device and more just to help us later in the future lessons. So we will say we are concave up from negative infinity until -1, and from 1/2 until positive infinity. And of course we will be concave down on the other interval from -1 to 1/2. Actual points of inflection, P dot I, will occur at both -1, comma, and now I go all the way back to here, and I'm looking for the y coordinate by using the original function f. -1, comma, -2. We have a point of inflection because f is differentiable at that point, and because f changes concavity from concave up to concave down at that point. And this is also a point of inflection. We change concavity from concave down to concave up, and f is differentiable. 1/2, comma, 1/16 plus 1/8 is 3/16, minus 3/4 is -9/16, plus 1/16 is 7/16. That's all there is to it. It should feel very familiar because it's the same exact process as finding intervals of increasing and decreasing behavior. Relative maxes and mins. Next, if f is this and f double prime is this, list the intervals, blah, 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 blah. I want to be clear. Sometimes the AP test will give you an f double prime because if a student fails to use the quotient rule here, then they have no hope of getting the rest of the points. So be careful, use what's given to you. Don't waste time verifying it. The first thing we want to check is the domain of f. And we should see that f has two problems when x is positive or -2. Both will be asymptotes. Hint. We do not need to find f double prime. We will start with f double prime of x equals 0. That will be true when, oh look, f double prime is a fraction. So when the numerator equals 0. Now, depending on who you are, you can stop this process at any time. Some people would stop here. Some people would start here. Others would stop here. And here's where I'm going to stop. We have a square equaling a negative number. That's not possible for real numbers. So this is not possible. There are no critical numbers like this. Please make sure you do not take the square root of both sides. You will lose points left and right. However, f double prime of x will be undefined when the bottom of that fraction equals 0. Cube root both sides. Factor. So we have two possible points of inflection, potentially. Sorry, I want to write them out as a list. We considered the domain. Oh no, both possible points of inflection are not in the domain. Domain F. So there are none. There are no possible points of inflection in actuality. However, when we make our f double prime number line, we will still put them on here, because just like before, we will consider these to be relevant to our sign analysis, just like in lesson 4-2. Go back and watch that if needed. So, to signify that they are domain restrictions, I will make asymptote type shapes. And now we will go through and check those signs in f double prime. Again, it's helpful to notice here that the top is always positive. So that way we're just checking the sign of the bottom. -3 squared, 9. 9 minus 4, positive. Positive cubed is positive. Positive over positive. 0. -4 cubed is going to be negative. Positive over negative is negative. 3. 3 squared positive. 9. 9 minus 4 positive. Positive over positive. And again, we will draw concavity shapes possibly to help us out. So we have in intervals where we're concave up, -infinity to -2, and from 2 to infinity. We will have intervals where we are concave down, from -2 to 2, but we will have no points of inflection. Why? Because the two places that look like points of inflection, the two places where concavity does in fact change, are not actual points on the graph. They are domain restrictions, so there is no activity there. You should be able to work on any problem on 4-3 now that does not say the word second derivative test, which will be covered in the next video. Thank you for your attention. Good luck on some problems. Have a great time with them. Bye for now.